Now, there are some indifference formulas other than the one we saw in the last video, right? We just focus on one formula. There's actually 4 of them for cosines and sines, and I have them listed here. And again, if you need to, pause the video, write them down so you have them. There's been a lot of formulas in class, so it is a good idea to kind of keep a stack of note cards or even just one running page of formulas that you think you're going to be using a lot. And again, these are good ones to have as easy reference. So you have cosine of the sum of 2 angles, which is very similar to what we just saw, but there's going to be a minus sign in between. And then cosine of the difference of 2 angles we've already worked with, again, has that plus sign in between. Now your sine formulas are a little bit different. So when you're adding the angles, you have sine alpha cosine beta plus cosine alpha sine beta. And then when you're subtracting them, you have sine alpha cosine beta minus cosine alpha sine beta. But they work the same way we saw in the last video. It's just a matter of applying the right formula. So here's an example. We're going to find the exact value of sine 7 pi over 12. And they're giving us a little hint here. They're going to remind us that, well, 7 pi over 12 is actually pi over 3 plus pi over 4. And these are common angles that we know. So again, the key here, why these are important, is because you would use them with common angles that you know, and that's what makes them useful. So we're going to go ahead and apply the formula here. Now we're going to notice that we're using sine, and we are adding the angles. So I'm going to be using this formula here that has addition of the 2 angles with our sine function. So sine of 7 pi over 12 is the same thing as sine of pi over 3 plus pi over 4. Now these formulas work both with degrees and radians. So here we're doing an example in radians. So this is my alpha, this is going to be my beta, and I'm using the addition formula. So it's going to be sine of pi over 3 times cosine of pi over 4 plus cosine of pi over 3 times sine of pi over 4. Now, again, these should be angles that you are familiar with, or if you're not, you have them easily accessible on like a note card or a table written down somewhere. So sine of pi over 3 is root 3 over 2. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 3 is 1/2. And then sine of pi over 4 is root 2 over 2. Here I multiply together, I get root 6 over 4. Here I go ahead and I multiply together, I get root 2 over 4, which gives me root 6 plus root 2 4. Okay, let's go ahead and do another example. I think I'm going to get a new sheet here because it's going to be a little bit of a longer problem, but I do want to refer back to these. So let's suppose that sine of alpha is 12 over 13 for a quadrant 2 angle alpha, and sine of beta is equal to 3 over 5 for a quadrant 1 angle beta. We're going to find the exact value for the following. Sorry, I'm writing sideways. For the following. So we're going to do cosine of alpha, cosine of beta, cosine of alpha plus beta. Then we're going to do sine of alpha plus beta here. Now this example is a little bit different than the last one because you actually don't have the angle, right? We actually have the lengths of the sides. You can think of it as in a triangle form. We don't actually have the angle. So I'm going to start by drawing a picture here just to see what I have. And I'm going to do this one first. So I do know here that, I'm just getting some of my colors out. I'm in quadrant 2, which is important. So my angle is, I'm not going to focus exactly on where it is, but somewhere in quadrant 2. And I do know that this is my alpha. This is my alpha. And I know that sine of alpha equals 12 over 13. Well, we're not in quadrant 1 here, so the triangle is not quite as straightforward as if it was in quadrant 1, but we do have our formulas here when we're not in quadrant 1. And remember that the formula here is y over r. So y being your y value of that point and r being the radius. So maybe our point is right here. So the radius here would be 13, and then our y value in this case would be that 12. Excuse me. So I can use this to go ahead and find my cosine. Cosine of that same angle would be x over r instead. Now I know what the r is. I know the r is 13, but I don't know my x value here. So it would be this value right here. But I can use the Pythagorean theorem. So I do know that x squared plus y squared is equal to r squared. So x squared plus 12 squared equals 13 squared. So I have x squared plus 144 equals 169. And I can subtract 144 from each side. And I get 25. And then I get x is 5, taking that square root. And again here, I know we're on the left side. So I mean, the point here would be a -5 in this case. But if we're looking at just the length there, it would be the positive for that length. So we want to be careful here. So our length here, and not right this way, our length here is 5. But again, because you're in that quadrant, the value here would be -5. So our x value is going to be -5 in this case, because we're going towards that left. So our answer here is going to be -5 over 13. So we're able to find the answer to A. Now we're going to do something similar, but for the second example, we're going to use beta. So again, I'm just going to draw the picture here. And for our beta angle, it's going to be in the first quadrant, which makes things a little bit easier. Oh, I guess I should use a different color. Let's call this our point. And we know our sine is going to be 3 over 5. So this is our angle here. And again, this is going to be our x. Here's our point. And I know that sine of beta is 3 over 5. Remember, that's y over r. So we're giving the r here is going to be 5. Our point is xy, so our y value here is 3. So this side is going to be 3. And then we're able to go ahead and finish this. So we're looking for cosine of beta, which is x over r. I know the r is 5, but I do need to complete the triangle. So x squared plus y squared equals r squared. So I have 9 equals 25. And when I subtract both sides, I do get 16. So our x value is 16 here, meaning the length, the x value is square root of 16, which is 4, meaning the length is 4. But think about it for a second, you're in the first quadrant, so your x value on that point would actually be positive. So our value here is positive 4 over 5. So we're able to answer the first two questions just actually using some things we already knew how to do. So using our triangles or using our plane to help us graph and figure out what each of these values are. So now I can go ahead and use my new formulas to find my cosine and my sine of those two. And I think I'm going to get, go to the next piece of paper. All right, so we're looking for cosine of alpha plus beta. And I could go to my formula here. So I'm going to use this formula right here. I'm just going to recopy it first. So the formula for addition is going to be cosine alpha times cosine beta minus sine alpha sine beta. Now here, remember, I don't actually know what the alpha and the beta are, but I do have all the answers now. So we know that cosine alpha, we found this in part A, that was -5/13. And cosine beta we found in part B was 4/5. Minus, now sine alpha was given to us at the start of the problem. That was way up here, 12/13. And then sine of beta was 3/5. Now you're going to just do a little bit of algebra here, and I've kind of done this already for us and just found the answer. And what you're going to get is going to be -56/65. So that is our final answer for that first one. For D, we're looking at sine of alpha plus beta. So again, I can just go back to my table here and write in my formula. So I'm just going to go ahead and copy that formula right in. So I'm looking at sine alpha times cosine beta plus cosine alpha times sine beta. So my sine alpha that was given to us, our sine alpha was 12/13. Our cosine beta we found, and that was 4/5. Our cosine alpha we found, that was -5/13. And then our sine beta was given to us, that was 3/5. And again, you're just going to do a little bit of arithmetic here. I'm going to save us the time. And you get 33/65 as your final result. So there we are able to answer that question, kind of applying some old techniques and also some new techniques here. Let's do one more example. All right, so here's an example we have. We're going to describe y equals sine of x minus 3 pi over 2 using another equation. So here we have the sine equation that has been shifted. We have a horizontal shift here. So I'm going to use our new formulas here. I'm going to use the difference of two angles, and I'm going to go ahead and rewrite that and use that here to answer this question. So remember, sine of alpha minus beta is sine alpha times cosine beta minus cosine alpha times sine beta. So here, my alpha is going to just be x, and my beta is going to be 3 pi over 2. So this becomes sine x times cosine of 3 pi over 2 minus cosine x times sine of 3 pi over 2. Now, 3 pi over 2 is actually a common angle. That's your 270-degree angle there. So again, that's one you should know. I can't do anything with the sine x though, so that's just going to stay sine x. And then cosine of 3 pi over 2 is actually 0. And again, I can't do anything with the x cosine x here, but sine of 3 pi over 2 is going to be -1. So 0 times sine x, that's just going to cancel out. That's just 0. Here, my two negatives cancel, and I'm left with just cosine x. So actually, the equation y equals sine of x minus 3 pi over 2 and y equals cosine x are the same here. So we're able to use that formula to actually find a new way to write a different equation that we could use here to mean the same thing. Now, the other thing you could do is also verify this with a graph. So if you were to graph this equation in this equation, you should see that they're going to run the same picture there. And let's see if I can do that really quick with you guys. Sorry, bear with me one second. I should have had this ready to go already, but I did not. So I'm going to turn off the blue one for a second here. Oh, I didn't mean to erase it, but I did. So there is the original function, sine of x minus 3 pi over 2. So I graph that one. And then I can also graph cosine x, which we said was the same. And you can see that when I graph it, it lies right on top, right? So there's the original graph. And then when I graph cosine x, it just goes right on top. So we can see that they really are the same equation, both algebraically using these formulas, but also graphically. So graphing is really a great tool for so many different things, but it's also great just to check your work and make sure you haven't made a mistake. So if you want to actually show that two things are the same, you could come in and graph them as well and make sure that you actually get the same graphs, right? So just a good way to go ahead and check that too.